And picking up on exactly what you said, what we're going to be discussing now is precisely that when it comes to fossil fuels, fossil energy, the problem is perhaps not so much that we're running out of coal and oil and other fossils, but that we need to accelerate the switch, whether or not we have more fossils left in the ground to burn. And an expert on that switch, and on not just doing it the way politicians often think we should switch to fuels in the car, but making sure that we do it in terms of materials, is Professor Ulrica Edlund at the Fiber and Polymer Technology at KTH in Stockholm. And she's been involved in so many different areas of going from non-renewable to renewable, including films, coatings, hydrogels. And if I were to mention all the prices you won, her 15 minutes would be up. So instead I'm going to let you understand why she won all of those prizes. Ulrika.
Thank you so much. So if you think about it, human life has always been strongly influenced by the materials that we use. I mean, we even divide eras in human history into parts like the Stone Age, the Bronze Age. So clearly materials define us and shape us in the process. And also strong leaps in technology has always been intimately connected to new discoveries of polymers. So what material age are we in today, you would say? Well, for sure, we're in an age where more people than ever before are sharing this planet, wanting same access to natural resources, and in all fairness should have equal access to our resources. We're at an age where obviously polymers and polymeric materials are ubiquitous. Plastics, rubbers, they're everywhere, from household products to the highest tech innovations. So we're at a polymer age, and we're at the advanced polymer age, because now, to a more sophisticated level than ever, we can actually engineer material structures and properties down to the nano and even the molecular level. So I dare say that in combination with some key element ages like silicon and aluminum, we're also at the advanced polymeric age. But at the same time, we're at an age where we can clearly see the negative consequences of our consumption and humans' quite careless use of natural resources. We're at an age where there's a global movement towards a more sustainable take on innovation, technology, and everything that we do. So, the question is, how can we use our skills in the advanced materials field and take a more sustainable action in terms of material science? Well, first we have to ask ourselves, what is really material sustainability? And first and foremost, I'd say it's a personal responsibility to rethink our own consumption pattern. The question to always ask ourselves every day is, do I really need this product? Do I really? Is it fair to use raw materials for this particular product for me? Well, many times the answer is actually yes. In the interest of hygiene, health, food quality, communication, transport, we do need products. And those products have to be made from something. So we need materials. Indeed, we need raw materials to make materials. So that brings us to the next set of crucial questions that we have to ask ourselves in order to get a more sustainable take on materials. What do I make the materials from? What raw materials are most sustainable to use? And how about the material health? What are the material safety? How about the components? How about all the chemicals and processes and steps in the technology that are used along the way to produce these polymers? That's another issue of material sustainability. And how about the fate of this material and this product in the post-consumer stage? What am I doing? This is where this takes action from our side. Do we design for recyclability? Do we design for degradability? Do we design, or do we have a strategy for how to reconsider waste as another set of raw materials? How can I reuse the material and its constituents one more time? All those things are questions where all of us that work in the material science can actually make a contribution, and that we try in our own ways and different approaches to make a bit more of a sustainability idea on how to produce materials. So we can, of course, approach this challenge in many ways. And what I would like to share with you today are some of the approaches that my colleagues and I take on trying to add sustainability to materials development. So particularly what we do is to rethink what raw materials that we use for polymer production. Now, polymers are to a very high extent made from fossil oil and from cracking of fossil oil. And what we are trying to do is to go from fossil-based to bio-based. Now, what's the challenge in that, you may ask? I mean, human has always led a bio-based life, right? The past century was just a brief exception to that. We've always been bio-based. That's all that we had. Yes, for sure. But along with the discovery of how to crack fossil oil and the discovery of how to use the fossil oil components to make synthetic polymers came something that we never saw before. Advanced structures, materials functions that we never seen the likes of before. And we got spoiled, and we improved our lifestyle, and we got dependent on those polymers. So the challenge is not so much to go bio-based. The challenge is to go bio-based and maintain the high level of material sophistication that we are demanding on an everyday basis. So the situation today is that a daunting 300 millions of polymers, plastics, are being produced yearly in the world. 300 millions. And only a tiny fraction of those are made from renewable resources, roughly 1%. So that's our challenge, to go back and increase that little tiny piece of the pie into a great piece of the pie being bio-based, and do that and still being able to provide a high level of material sophistication. Do that? Well, yes, we can actually. But it's important to think about what biomasses that we use. What biopolymers rest in the different biomass, to get a solid understanding of that, and of course the potential properties that hides in those biopolymers if we're able to extract them and use green processes to make that. It's also important to choose biomass that are not competing from an ethical perspective with the production of food and feed. There's a lot of biomass. There's enough biomass for everybody. So let's find those that are not already being in high demand in food production. We also need to use the biomass efficiently. And this is an area where we can really improve. Now, take wood as an example here. We have a very successful industry, not least in Sweden, where we on a commercial scale very successfully isolate the cellulosic component from wood and turn it in industrial process into a range of different products, paper, pulp, textiles. All right, but cellulose is only constitutes about a third of wood. That leaves 2/3 of other biopolymers that in a pulp plant like this is not really valorized. So we can learn a lesson from the fossil-based industry. Just like they do refining to crack naphtha into a range of valuable products, we can look at biomass as the crude oil, and we can biorefine it into a platform of different valuable products that we can use for bio-based materials, but also for platform chemicals, for fuel, for textiles, for food, for feed. And this is really the essence of a biorefinery, to make more from less. I'm echoing what you said earlier today, but this is really what it's all about, to use the biomass more efficiently so that we get more out of each volume or fraction of biomass that we use. There's another thing we need to do. We need to understand the polymers, because only in that way we can use them wisely. So we have to penetrate down and understand the chemistry from the fundamental level, to understand the structure property relationships, and then we also can have a strategy for how to use them in the best way and in the most efficient way. And this is where new infrastructure like the MAX4 can really help us advance in this field, because now we have a chance to even better understand the chemistry and the chemical interaction in these molecules even better and help us make more sophisticated materials in the future. So let me show a few examples of how we can turn biomass fractions and biopolymers into successful products. All these products are based on hemicellulose fractions. They are residues from cellulose processing plants, such as board factories and pulp factories, where hemicelluloses are being released to the effluents from where they can be isolated, refined if needed, and turned into a range of different materials. So we have been making bioplastics, highly water-absorbing hydrogels, electrically conductive systems, magnetic systems, heavy metal absorbing filters, and so on. There's just goes to show that there are a number of different things that we can do from biomass components without having to compromise with advanced material function. So inspired by this, a wood biorefinery outcome, we started to look at other types of biomass. So we heard a little bit about oilseed before. Now oilseed is also successfully grown in Sweden, especially rapeseed, which we use commercially successfully to make oil for food and feed primarily, but there's also an increasing attention now to rapeseed oil for making biofuel, the RMEs, that are being used on a more extensive basis these days. So this is a good business, but in this process we only utilize the seeds. That leaves us with about 1.5 meter of hard and rigid woody stem that is being left on the field and not valorized at all. And this is what we're trying to change. So we're building a biorefinery process around this, where we make use of those stems, we fractionate it, and we are able to isolate 3 individual fractions of biopolymers that then can be individually processed and turned into different materials. Like in this case, we make bioplastics, but we also make fibers, and we make this textile fluff from the cellulosic residue. And if we can do all that from terrestrial biomass, just think about the huge potential that rests in marine plants that we're not actually utilizing at all. There's plenty of room for cultivation or agriculture at sea. You don't even need extra water irrigation. It's all set. And there are many macroalgae that thrive on the west coast of Sweden. That's the natural habitat. And we're not utilizing them at all. And we're trying to change that. So we are working with several kinds of biomass. Those are being either harvested wild or cultivated. And then we try to design a biorefinery process, and we can fractionate several different valuable components. So we can make use of proteins and lipids in the food and feed additive industry. We can make use of small molecules in the platform chemical industry. And this is my part, we can make use of the biopolymers as a raw material for polymeric products. This sounds really straightforward and fun, and it really is fun, but for sure it's not straightforward, because building a true biorefinery is a really complex business. It's not just about having a green resource, the biomass, or in the end producing a green material that's based on natural resources. Everything, every step along the way has to be green. And that takes really an interdisciplinary effort of the more major kind. We need to rethink every single step of this process: transport, energy consumption, chemical demands, and so on. So what we're doing in this case is to build a broad transdisciplinary consortium in which we try to address every different part of the biorefinery. So we have the marine biologists at Göteborgs University that look into all the aspects of cultivation, growth, harvest, transport. The biomass goes to Chalmers, biotechnology and food chemistry, and where they're looking into the first storage and fractionation. Can we make something from the proteins and lipids? We also, in this biorefinery process, have myself and KTH involved in looking at the biopolymers. The residues from the biorefinery is not a waste. It's a raw material for the next step in the biorefinery, and that would be the biogas production at Växjö, Linnéuniversitetet. And their residues are the nutrients that can be fed back to the cultivation, closing the loop. And then we have to evaluate each and every step of the process for socioeconomic, economic sustainability, technical sustainability, and so on. And that's being done by Lund and KTH in life cycle analyses. So a biorefinery can really be a solution to how to provide us with more biomass and raw materials, but it has to be done thoroughly, and it's a complex process. But still, in essence, this is really the message that I want to convey to you today, that it's possible, that biorefining is one way to provide us with more raw materials in the future, and the essence of the concept is to make more from less, and that we feel is at least one contribution to making materials more sustainable in the future. Thank you.
Thank you so much, Ulrica. You were on the second, as exact as your research. I'm thinking that one of the main winners in closing the loops is, of course, the climate.
Mm-hmm.
And I'm thinking that when we, for instance, your example of rapeseed, that's interesting for us living here in the south of Sweden, where we have a lot of rapeseed fields. Mm. It's incredible how wasteful we've been. How is that even possible to be so wasteful?
Well, that's a question that I think each and every one of us have to answer.
Yeah, that's true. That's a question that begs for answers from all of us.
Can we afford to be wasteful? Have we been wasteful? Yes, we have. So I guess what we can do is to just move on from here. How can we be less wasteful in the future?
And that everyone has something that approaches a rapeseed field. Well, we're going to find, if we take a closer look, that we are so wasteful and there's so much resources out there. Mm. Thank you ever so much, Ulrica.